So we've already looked at sets of points, and we've also looked at equations. And now I want to talk about graphs with you guys, which is another way that we can express relations and then also functions. So let's focus on graphs. With function notation, we know that y and f of x mean the same thing. They are equivalent. And I've already showed you that when we graph, we can change that function notation into points. So if you have something like this, f of x equals y, well, you can also rewrite that as the point x comma y. So just to use a random example, if I have f of 2 equals 3, this is the point 2 comma 3. The inside value is your x, and the outside value, that would be an output, that would be your y. So we can graph functions, basically doing the same thing we already have by just picking values to plug in. So let's make a little table here. And we're going to use integers from -2 to 2. And one other thing I do want to note here, so notice how one of them we used f of x and the other we used g of x. That is still function notation. So this still represents a function there, just that we give it different names. So instead of everything being f of x, we'll use different letters, f of x, g of x, h of x, j of x, really whatever you want. F and G and H tend to be the most common, you'll see. But if you have that symbol, no matter what letter it is, it still means function notation. So what you're going to do here is just go ahead and plug in. So you're going to take your x value here and just replace it. So for the first one, f of -2 is just 2 times -2, which is -4. F of -1 is 2 times -1, which is -2. F of 0 is just 2 times 0, which is 0. And then we can do the other ones out. I think f of 1 would be 2 times 1, which is 2. And f of 2 would be 2 times 2, which is 4. So we're still just plugging in values like we have before. And I would do the same thing for g of x. So if I'm doing g of -2, it's 2 times -2 plus 4. -4 plus 4 is 0. G of -1 would be 2 times -1 plus 4. I'm just plugging right into the expression there on the right. -2 plus 4 is 2. G of 0 is 2 times 0 plus 4, which is 0 plus 4, which is 4. Running out of room here. Let's see. G of 1 is 2 times 1 plus 4. So 2 plus 4 is 6. And then G of 2 is 2 times 2 plus 4. So 4 plus 4, which is 8. And then we can graph those the same way. So for our first example, we have, let's see, -2, -4, -1, -2, 0, 0, 1, 2, and 2, 4. And I'm just going to label that f of x. And I will do g of x. So at -2, I'm at 0. -1, I'm at 2. 0, I'm at 4. Let's see, 1, I'm at 6. And then 2, I am up here. Let's see, 5, 6, 7, at 8. And those would be our two functions. Now you can also graph in Desmos as well. So just a fun little tip, I'm not going to bring it up here in this video, but if you go to Desmos, you can either type in with y. So you could write y equals 2x or y equals 2x plus 4, or you can type in with function notation. So if you type in Desmos f of x equals 2x or g of x equals 2x plus 4, it can typically handle all that notation as well, which is really nice. So you can give that a try at home with Desmos too. Now, there's also a test to decide if a function exists just from a graph. So let's say you don't have an equation, maybe you have just the graph instead. How can you decide if something is a function? And that uses the vertical line test. So the vertical line test says that if any vertical line intersects the graph more than one point, the graph is not a function. So you're seeing actually the same thing. If you intersect the graph more than once through any vertical line, then you have the same x values going to different y values. So you're getting those repeats. Let me do a couple of examples here. I'm just going to draw them in. I thought it'd be easier. Let's see, A, B, C, and D. Okay. So here are just 4 different graphs. And to test if something is a function, we're going to use the vertical line test. So what I like to do is I like to physically draw in vertical lines, and you can draw them anywhere you want on the graph. And you're looking to see if a vertical line touches more than once. And as soon as if you find one, you can stop. So see how this line touches more than once? This one also touches more than once. Something like this is not a function. Okay, because it touches more than once. I don't care about the axes, I just care about the graph. Because basically what's happening is this. For instance, let's say this is the value x equals 1. Maybe this is the value y equals 1, and this is the value y equals -1. And what happens is you're seeing that the same x value is going to 2 different y values. That's what's happening here. So it's still the same definition, that x value is repeating, it's going to different y values, it's not a function. In B, if I draw vertical lines through, I'm only going to hit that graph one time. So something like this is a function. So what's happening is that each x value only has one y value with it. Same thing would be true here. No matter where I draw a vertical line, it only touches once. And then this one we're going to see is a problem. Now, there's no issue here. There's no issue here. It only touches once. But anywhere else I draw a line on the right of that, I'm going to hit that graph more than once. If you can find one vertical line that doesn't work, then it's not a function. So this vertical line hits twice. So this is not a function. Okay. Another thing that's nice too is when you have an equation, if you're kind of getting stuck on deciding is an equation a function by solving for y, you can always graph it. So graphing is a great way as well to look to see if something is a function, particularly if you have a more complicated equation, maybe one that you can't solve for y or you're having really hard time with, just graph it, leave it in the form it's in, go to Desmos, graph it, and then use your vertical line test. And that's really a nice thing to do as well. Okay. So just make a little note, good for equations too. So you can always graph these if you're getting stuck. Okay, let's talk a little bit more about graphs. So just a couple key things that I think everybody knows, but just reminders. So on a graph, if you see a closed dot or like a point, just remember that if it's at the end of the graph, that means the graph does not extend beyond that point. But a closed dot means that you include that point on the graph. If you have an open dot on your graph, then the graph goes until that point, but that open point is not included. It's actually like a little skip over on the graph. And of course, if you see arrows at the end of your graph, then you would assume that it keeps continuing in either direction, whichever way the arrow is pointing. So for example, before we even look at this example here, see how there's an endpoint there and an endpoint here. So this graph does not continue indefinitely. Whereas our other examples, over here, when you see arrows, you know that it keeps continuing in the same pattern or in the same direction. So if you don't have those, if you have some sort of endpoint, then it's going to stop. Because the endpoints are closed, so they're filled in, then those points are part of our graph. If you have a hole though, like, so for instance, let's say your graph looks like this. And then there was an open circle here. So your graph would go until that point, but it would not actually include the endpoint here. So that would almost be like a strict less than or greater than idea. Here, less than, if you see an open circle. So you go up until that point, but technically that endpoint is not on the graph. We don't see them too often, but we do sometimes see them more so with more complicated examples. And sometimes in the middle of graph, we'll kind of skip over points if we need to, which happens a lot if something is undefined, if we're dividing by 0 or something like that. All right, so let's look at our example here. So the human, our HIV infects and kills helper T cells. Because T cells stimulate the immune system to produce antibodies, their destruction disables the body's defenses against other pathogens. By counting the number of T cells that remain active in the body, the progression of HIV can be monitored. The fewer helper T cells, the more advanced the disease. Without the drugs that are now used to inhibit the progression of the virus, the figure shows a graph that is used to monitor the average progression of the disease. The number of T cells, f of x, is a function of time after infection. So again, this is without drugs. So if there was no, medical intervention here to help prevent the progression of the disease, you can see here's the starting value. Before the person is infected, they would be up here maybe close to 1200 for their T cell count. Then they have an initial drop off. They may have gained a little bit more, and then you're going to see a steady decline here. So let's answer the questions. First, we're going to explain why f represents the graph of a function. And the way we can do that is you can use your vertical line test. So if I use my vertical line test and I try to draw vertical lines all through this, if I draw a vertical line here or here or here, I'm only ever going to hit the graph one time. And I'm not going to write all over here because I want to be able to talk more about it on the video, but try it at home. Use a pencil or a highlighter or something and just try to draw vertical lines. You're not going to hit more than once. Even here, it looks like maybe it would be, but it's not perfectly vertical. So if you draw a line, it's still just going to hit only one time. So it does pass the vertical line test. So for B, we're looking at f of 8. So that inside value, remember, is your x value. So we're looking at 8 here for our x value. So here's x is 8. And if I go up, I can see that my point looks to be about 200. So f of x looks to be about maybe 200. So 8 is in years. So after 8 years, and then y is your T cell count. The T cell count is about 200. Now I like C as well. C is a little bit different. We haven't seen something like this yet. And it says f of x equals 300. Now in this case, you're not given the x value. Remember that your outputs are always your y's, right? So this time you're being given the y value instead, and you're going to work backwards to the x. If you ever have an example like this, so let's say your function was f of x equals 2x plus 4, and you were asked to find f of x equals 5, for instance, then what you're going to do is remember that this is your y value, and you're going to go ahead and set that whole function equal to 5 in this case. And then you would keep solving. So here we're looking at y equals 350. So I'm going to find 350 on my graph, which is about maybe like right here. And I'm going to go over and see if I can match it with a point. So it looks like it could be around 6 years here. So when x is equal to 6, then your y value is equal to 350. So after about 6 years, then the T cell count is about 350. Now for part D, let's just talk about the general trend here. We don't have to write this out. You can just see overall that general trend is decreasing, right? So you have a little bit of uptick here. So initial drop off, then maybe a little bit of uptick. So this is what they're saying is the asymptomatic stage. So you have very few symptoms. But then over time, overall, you can see that that T cell count really just drops over time. So that general trend for most of it anyway is a decreasing graph. Okay. So the last thing I want to do in this video is talk about domain and range with graphs. You can also find domain and range for graphs. For domain, remember that these are going to be your X values or whatever is on the horizontal axis. So you want to think in a left to right direction for domain. And then for your range, these are your Y values or whatever's on the vertical axis. So you want to think in a down and up direction. And you want to just think one direction at a time. I actually usually like to use a pen or a pencil while I'm doing this just to help me stay focused. So I'm going to just start and go in order. I'm going to do A first. And remember, your domain, those are your X's. So you're looking left to right. X axis goes left to right. So you're just focusing on left to right. What values does my graph cover? So if I go left to right, I see that I stop at -2 here, right? That's the farthest my graph goes. And I go all the way to +1 on the right. So those are my X values. Now my endpoints are included. See how they're closed circles? So we include the endpoints. So either we can write it like this in interval notation, -2 to 1, right? And I'm using brackets because those endpoints are included. Or you could write it in set notation. X is less than or -2 is less than or equal to X is less than or equal to 1. And again, I'm using the equal sign because my endpoints are included. Your range is your Y value. So you're thinking in a down to up direction. So now you're just looking at Y's. Don't think about the X's here. Just think down to up. So in the downward direction, I stop here on the X axis. So that would be at Y is 0. And in the up direction, I stop at Y equals 3. And again, those endpoints are included. So I'm going from 0 to 3. That would be our interval notation. Or if you want to write it in set notation, it would be 0 to 3 this way. Don't forget you're using Y's now. So just change your variable. Let's do the next one. So now I'm going to go ahead and do B. And again, I'm going to start with my domain here. Domain is just left to right. So only think one direction at a time. So on the left, my graph stops at -3. And on the right here, my graph stops at 2. You want to be careful. There's an open circle at -3, which means that we're not including the endpoint. So when we're not including the endpoint for interval notation, you're using parentheses. Or if you're using set notation, it would be -3 is less than X is less than or equal to 2. So notice that when endpoints are included, I'm using the brackets or the equality piece. And when the endpoints are not included, I'm using the parentheses or the strict less than or greater than. For our range, I'm just looking in a down to up direction. So my graph goes as low as 1 and as high as 2. But again, this point is not included. So I go from 1 to 2. Or 1 to 2. Okay. C, we're going to do the same thing. So for domain, again, left to right only. So on the left side, we go all the way to here, which is at X is -2. On the right side, we only go to 1. Now notice that my left side is included. My right side is not. And then for our range, we go down to 1. Now there's no endpoint there, but it touches 1, so that's going to be included. And it goes up to 5. Now I know there's a hole here, but when we go upward, we do actually hit the 2 values. See how we hit it over here? So all those values in between are included. So I'm going from 1 to 5. This could be a good time to pause the video and try some on your own. So let me go do D and E now. So for D in the left to right direction. Now notice it stops at 4 on the right, but it keeps going left forever. So think about it. If you're going left forever, you're going towards the negatives. So you're going to -infinity up until 4. Infinities always get parentheses, and this number will get a bracket because of the inclusion there. In set notation, you can just write this as x is less than or equal to 4. In the y direction, think just down and up. It goes down, it stops on the x-axis, which is at y equals 0. Now, if you think about it, this line keeps going up, 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 up. It goes up slowly, but it's going to go up forever. So we're going from 0 to positive infinity. So y is at least 0 here. 0 gets a bracket because the endpoint is included. Infinities always get parentheses. So think back to your interval notation. Okay. Now this next one's a little bit weird. This is actually an example of what's called a step function because it looks like steps. So let's be careful here. So for my domain from left to right, I see I start at 1 and I end at 4. 4 is open circle, but I have these open circles in between. However, the values are actually included because even though the open circle is here on the 2, the closed circle above it includes the 2. So even though we're skipping over it here, we're including the value there. And same thing here. I know there's an open circle here, but the one above it also at x equals 3 includes it. So there's actually no holes in between for the domain in the sense that all the x values are counted somewhere on the graph. So our domain starts at 1 and it ends at 4. Okay. And again, I know there's holes here, but because x equals 2 is represented here and x equals 3 is represented there, we can include all values in between in our domain. For the range, this one's a little bit tricky. So think down to up. So I go down to 1 and I'm up to 3, but I definitely have holes in between. If you look, there's nothing here, right? There's nothing here. So I'm actually not including the full range of values. I'm skipping a lot. If I look at my y values, there's only 3 answers. Y equals 1, y equals 2, and y equals 3, right? Here's the 1, here's the 2, here's the 3. So for my range, I'm just going to use set notation here, 1, 2, and 3. Okay, so that one's a little bit different because you can't really include everything in between. It's not all included. So we're going to use a set notation there instead. Now for the other ones, I'm just kind of using the more informal set notation, but do remember that for any of these, you can be a little bit more formal. So here, I could write this as the set of x such that 1 is less than or equal to x is less than 4. This can be written as the set of y such that y is equal to 1, 2, or 3. So if you see that more formal notation in your text, you can use that too. I'm just doing the more informal notation for set notation here. All right, finally here, just as a little note, we have already seen that we can identify x and y intercepts from graphs, right? We know how to do that. And the same is true with graphs of functions. So you can also, same way that we have before, it's the same definitions for identifying intercepts, whether you have a function or not a function from a graph. We do have a new terminology here though, and we say the zeros of a function. So the zeros of a function are the x values for which f of x is 0. Thus, the real zeros are also the x-intercepts. So that term zeros and x-intercepts are basically used interchangeably as long as the values are real. Of course, you could have zeros of a function that are imaginary or complex, which you would not see in a graph. But if it's a real 0, then you're going to see those on the graph as your x-intercepts. One thing to note for answers. So if, for instance, let's say 2, 0 and -5, 0 are x-intercepts of the function, then you would say the zeros of the function are 2 and -5. So when you say zeros, we do not usually put it in point form. We usually just say the number. So you just want to be careful of that when entering your answers. So if something asks for a 0, you would just say, oh, the 0 is 2. The 0 is -5, instead of writing the full point. One last note, a function can have more than one x-intercept, but if it is a function, it would only have one y-intercept. If something is not a function, it can have more or less, but if it is a function, it would have at most one y-intercept.